Combustion or burning is the sequence of exothermic chemical reactions between a fuel and an oxidant accompanied by the production of heat and conversion of chemical species. The release of heat can produce light in the form of either glowing or a flame. In a complete combustion reaction, a compound reacts with an oxidizing element, such as oxygen or fluorine, and the products are compounds of each element in the fuel with the oxidizing element. The process releases heat energy. Fuel plus oxidizer are combustion products plus heat energy, for example, CH4, G, plus 2O2, G, a CO2, G, plus 2 hours 2O, G. The standard enthalpy of reaction for methane combustion at 298.15 K and 1 atm is 802 kJ per mole. A simple example can be seen in the combustion of hydrogen and oxygen, a reaction commonly used to fuel rocket engines, 2H2, G, plus O2, G, a 2 hours 2O, G. The result is water vapor, with a standard enthalpy of reaction at 298.15 K and 1 atm of 242 kJ per mole. Another example is burning of carbon, which is the main component of coal, C, S, plus O2, G, a CO2, G. Complete combustion is almost impossible to achieve. As actual combustion reactions come to equilibrium, a wide variety of major and minor species will be present, such as carbon monoxide, hydrogen and even carbon. Additionally, any combustion at high temperatures in atmospheric air, which is 78% nitrogen, will also create small amounts of several nitrogen oxides, commonly referred to as NOx. Combustion need not always involve oxygen. For example, hydrogen burns in chlorine to form hydrogen chloride with the liberation of heat and light characteristic of combustion. Types: complete versus incomplete. Complete. In complete combustion, the reactant burns in oxygen, producing a limited number of products. When a hydrocarbon burns in oxygen, the reaction will primarily yield carbon dioxide and water. When elements are burned, the products are primarily the most common oxides. Carbon will yield carbon dioxide, sulfur will yield sulfur dioxide, and iron will yield iron, oxide. Nitrogen is not considered to be a combustible substance when oxygen is the oxidant, but small amounts of various nitrogen oxides form when air is the oxidant. Combustion is not necessarily favorable to the maximum degree of oxidation, and it can be temperature dependent. For example, sulfur trioxide is not produced quantitatively by the combustion of sulfur. NOx species appear in significant amounts above about 2,800 °C, and more is produced at higher temperatures. The amount of NOx is also a function of oxygen excess. In most industrial applications and in fires, air is the source of oxygen, O2. In air, each mole of oxygen is mixed with approximately 3.71 mol of nitrogen. Nitrogen does not take part in combustion, but at high temperatures some nitrogen will be converted to NOx, mostly NO, with much smaller amounts of NO2. On the other hand, when there is insufficient oxygen to completely combust the fuel, some fuel carbon is converted to carbon monoxide and some of the hydrogen remains unreacted. A more complete set of equations for the combustion of a hydrocarbon in air therefore requires an additional calculation for the distribution of oxygen between the carbon and hydrogen in the fuel. The amount of air required for complete combustion to take place is known as theoretical air. However, in practice the air used is 2-3x that of theoretical air. Incomplete combustion will occur when there is not enough oxygen to allow the fuel to react completely to produce carbon dioxide and water. It also happens when the combustion is quenched by a heat sink, such as a solid surface or flame trap. For most fuels, such as diesel oil, coal or wood, pyrolysis occurs before combustion. In incomplete combustion, products of pyrolysis remain unburnt and contaminate the smoke with noxious particulate matter and gases. Partially oxidized compounds are also a concern. Partial oxidation of ethanol can produce harmful acetaldehyde, and carbon can produce toxic carbon monoxide. The quality of combustion can be improved by the designs of combustion devices, such as burners and internal combustion engines. Further improvements are achievable by catalytic afterburning devices or by the simple partial return of the exhaust gases into the combustion process. Such devices are required by environmental legislation for cars in most countries, and may be necessary to enable large combustion devices, such as thermal power stations, to reach legal emission standards. The degree of combustion can be measured and analyzed with test equipment. HVAC contractors, firemen and engineers use combustion analyzers to test the efficiency of a burner during the combustion process. In addition, the efficiency of an internal combustion engine can be measured in this way, and some U.S. states and local municipalities use combustion analysis to define and rate the efficiency of vehicles on the road today. Smoldering slow. Smoldering is the slow, low-temperature, flameless form of combustion, sustained by the heat evolved when oxygen directly attacks the surface of a condensed phase fuel. It is a typically incomplete combustion reaction. Solid materials that can sustain a smoldering reaction include coal, cellulose, wood, cotton, tobacco, peat, duff, humus, synthetic foams, charring polymers, and dust. Common examples of smoldering phenomena are the initiation of residential fires on upholstered furniture by weak heat sources and the persistent combustion of biomass behind the flaming fronts of wildfires. Rapid combustion is a form of combustion, otherwise known as a fire, in which large amounts of heat and light energy are released, which often results in a flame. This is used in a form of machinery such as internal combustion engines and in thermobaric weapons. Such a combustion is frequently called an explosion, though for an internal combustion engine this is inaccurate. An internal combustion engine nominally operates on a controlled rapid burn. When the fuel-air mixture in an internal combustion engine explodes, that is known as detonation. Spontaneous combustion is a type of combustion which occurs by self-heating, followed by thermal runaway and finally, ignition. Turbulent combustion resulting in a turbulent flame is the most used for industrial application because the turbulence helps the mixing process between the fuel and oxidizer. Microgravity. Combustion processes behave differently in a microgravity environment than in Earth gravity conditions due to the lack of buoyancy. For example, a candle's flame takes the shape of a sphere. Microgravity combustion research contributes to understanding of spacecraft fire safety and diverse aspects of combustion physics. Microcombustion, combustion processes which happen in very small volumes are considered microcombustion. The high surface-to-volume ratio increases specific heat loss. Quenching distance plays a vital role in stabilizing the flame in such combustion chambers. Chemical equations. Stoichiometric combustion of a hydrocarbon in oxygen. Generally, the chemical equation for stoichiometric combustion of a hydrocarbon in oxygen is where Z equals X plus a 1/4 Y. For example, the stoichiometric burning of propane in oxygen is. The simple word equation for the stoichiometric combustion of a hydrocarbon in oxygen is stoichiometric combustion of a hydrocarbon in air. If the stoichiometric combustion takes place using air as the oxygen source, the nitrogen present in the air can be added to the equation to show the composition of the resultant flue gas, where Z equals X plus a 1/4 Y. For example, the stoichiometric combustion of propane in air is. The simple word equation for the stoichiometric combustion of a hydrocarbon in air is. Trace combustion products. Various other substances begin to appear in significant amounts in combustion products when the flame temperature is above about 1600 K. When excess air is used, nitrogen may oxidize to NO and, to a much lesser extent, to NO, 2. CO forms by disproportionation of CO2, and H2 and OH form by disproportionation of H2O. For example, when 1 mol of propane is burned with 28.6 mol of air, the combustion products contain 3.3% O2. At 1400 K, the equilibrium combustion products contain 0.03% NO and 0.002% OH. At 1800 K, the combustion products contain 0.17% NO, 0.05% OH, 0.01% CO, and 0.004% H2. Diesel engines are run with an excess of oxygen to combust small particles that tend to form with only a stoichiometric amount of oxygen, necessarily producing nitrogen oxide emissions. Both the United States and European Union enforce limits to vehicle nitrogen oxide emissions, which necessitate the use of special catalytic converters or treatment of the exhaust with urea. Incomplete combustion of a hydrocarbon in oxygen. The incomplete combustion of a hydrocarbon with oxygen produces a gas mixture containing mainly CO2, CO, H2O, and H2. Such gas mixtures are commonly prepared for use as protective atmospheres for the heat treatment of metals and for gas carburizing. The general reaction equation for incomplete combustion of 1 mole of a hydrocarbon in oxygen is. The simple word equation for the incomplete combustion of a hydrocarbon in oxygen is. For stoichiometric combustion, Z equals X plus a 1/4 Y. When Z falls below roughly 50% of the stoichiometric value, CH4 can become an important combustion product. When Z falls below roughly 35% of the stoichiometric value, elemental carbon may become stable. The products of incomplete combustion can be calculated with the aid of a material balance, together with the assumption that the combustion products reach equilibrium. For example, in the combustion of 1 mole of propane, c. 3 hours, 8, with 4 moles of O2, 7 moles of combustion gas are formed, and Z is 80% of the stoichiometric value. The three elemental balance equations are. These three equations are insufficient in themselves to calculate the combustion gas composition. However, at the equilibrium position, the water-gas shift reaction gives another equation. For example, at 1200 K the value of Keck is 0.728. Solving, the combustion gas consists of 42.4% H2O, 29.0% CO2, 14.7% H2 and 13.9% CO. Carbon becomes a stable phase at 1200 K and 1 atm pressure when Z is less than 30% of the stoichiometric value, at which point the combustion products contain more than 98% H2 and CO and about 0.5% CH4. Fuels, substances or materials which undergo combustion are called fuels. The most common examples are natural gas, propane, kerosene, diesel, petrol, charcoal, coal, wood, etc. Liquid fuels, combustion of a liquid fuel in an oxidizing atmosphere actually happens in the gas phase. It is the vapor that burns, not the liquid. Therefore, a liquid will normally catch fire only above a certain temperature, its flash point. The flash point of a liquid fuel is the lowest temperature at which it can form an ignitable mix with air. It is also the minimum temperature at which there is enough evaporated fuel in the air to start combustion. Solid fuels, the act of combustion consists of three relatively distinct but overlapping phases: preheating phase, when the unburned fuel is heated up to its flash point, and then fire point. Flammable gases start being evolved in a process similar to dry distillation. Distillation phase or gaseous phase, when the mix of evolved flammable gases with oxygen is ignited. Energy is produced in the form of heat and light. Flames are often visible. Heat transfer from the combustion to the solid maintains the evolution of flammable vapors. Charcoal phase or solid phase, when the output of flammable gases from the material is too low for persistent presence of flame and the charred fuel does not burn rapidly and just glows and later only smolders. Combustion management, efficient process heating requires recovery of the largest possible part of a full unregistered trademark S heat of combustion into the material being processed. There are many avenues of loss in the operation of a heating process. Typically, the dominant loss is sensible heat leaving with the OFF-gas. The temperature and quantity of OFF-gas indicates its heat content, so keeping its quantity low minimizes heat loss. In a perfect furnace, the combustion airflow would be matched to the fuel flow to give each fuel molecule the exact amount of oxygen needed to cause complete combustion. However, in the real world, combustion does not proceed in a perfect manner. Unburned fuel, usually CO and H2, discharged from the system represents a heating value loss. Since combustibles are undesirable in the OFF-gas, while the presence of unreacted oxygen there presents minimal safety and environmental concerns, the first principle of combustion management is to provide more oxygen than is theoretically needed to ensure that all the fuel burns. For methane, CH4, combustion, for example, slightly more than 2 molecules of oxygen are required. The second principle of combustion management, however, is to not use too much oxygen. The correct amount of oxygen requires 3 types of measurement: first, active control of air and fuel flow; second, OFF-gas oxygen measurement; and third, measurement of OFF-gas combustibles. For each heating process there exists an optimum condition of minimal OFF-gas heat loss with acceptable levels of combustibles concentration. Minimizing excess oxygen pays an additional benefit. For a given OFF-gas temperature, the NOx level is lowest when excess oxygen is kept lowest. Adherence to these 2 principles is furthered by making material and heat balances on the combustion process. The material balance directly relates the air-fuel ratio to the percentage of O2 in the combustion gas. The heat balance relates the heat available for the charge to the overall net heat produced by fuel combustion. Additional material and heat balances can be made to quantify the thermal advantage from preheating the combustion air, or enriching it in oxygen. Reaction mechanism: combustion in oxygen is a chain reaction in which many distinct radical intermediates participate. The high energy required for initiation is explained by the unusual structure of the dioxygen molecule. The lowest energy configuration of the dioxygen molecule is a stable, relatively unreactive diradical in a triplet spin state. Bonding can be described with 3 bonding electron pairs and 2 antibonding electrons, whose spins are aligned, such that the molecule has non-zero total angular momentum. Most fuels, on the other hand, are in a singlet state, with paired spins and zero total angular momentum. Interaction between the two is quantum mechanically a forbidden transition, that is possible with a very low probability. To initiate combustion, energy is required to force dioxygen into a spin-paired state, or singlet oxygen. This intermediate is extremely reactive. The energy is supplied as heat, and the reaction then produces additional heat, which allows it to continue. Combustion of hydrocarbons is thought to be initiated by hydrogen atom abstraction from the fuel to oxygen, to give a hydroperoxide radical. This reacts further to give hydroperoxides, which break up to give hydroxyl radicals. There are a great variety of these processes that produce fuel radicals and oxidizing radicals. Oxidizing species include singlet oxygen, hydroxyl, monatomic oxygen, and hydroperoxyl. Such intermediates are short-lived and cannot be isolated. However, non-radical intermediates are stable and are produced in incomplete combustion. An example is acetaldehyde produced in the combustion of ethanol. An intermediate in the combustion of carbon and hydrocarbons, carbon monoxide, is of special importance because it is a poisonous gas, but also economically useful for the production of syngas. Solid and heavy liquid fuels also undergo a great number of pyrolysis reactions that give more easily oxidized, gaseous fuels. These reactions are endothermic and require constant energy input from the ongoing combustion reactions. A lack of oxygen or other poorly designed conditions result in these noxious and carcinogenic pyrolysis products being emitted as thick, black smoke. The rate of combustion is the amount of a material that undergoes combustion over a period of time. It can be expressed in grams per second or kilograms per second. Temperature. Assuming perfect combustion conditions, such as complete combustion under adiabatic conditions, the adiabatic combustion temperature can be determined. The formula that yields this temperature is based on the first law of thermodynamics and takes note of the fact that the heat of combustion is used entirely for heating the fuel, the combustion air or oxygen, and the combustion product gases. In the case of fossil fuels burnt in air, the combustion temperature depends on all of the following: the heating value, the stoichiometric air-to-fuel ratio, the specific heat capacity of fuel and air. The air and fuel inlet temperatures. The adiabatic combustion temperature increases for high heating values and inlet air and fuel temperatures and for stoichiometric air ratios approaching 1. Most commonly, the adiabatic combustion temperatures for coals are around 2200 AA degrees Celsius, around 2150 AA degrees Celsius for oil and 2000 AA degrees Celsius for natural gas. In industrial-fired heaters, power station steam generators, and large gas-fired turbines, the more common way of expressing the usage of more than the stoichiometric combustion air is % excess combustion air. For example, excess combustion air of 15% means that 15% more than the required stoichiometric air is being used. Instabilities. Combustion instabilities are typically violent pressure oscillations in a combustion chamber. These pressure oscillations can be as high as 180 decibels, and long-term exposure to these cyclic pressure and thermal loads reduces the life of engine components. In rockets, such as the F-1 used in the Saturn V program, instabilities led to massive damage of the combustion chamber and surrounding components. This problem was solved by redesigning the fuel injector. In liquid jet engines, the droplet size and distribution can be used to attenuate the instabilities. Combustion instabilities are a major concern in ground-based gas turbine engines because of NOx emissions. The tendency is to run lean, an equivalence ratio less than 1, to reduce the combustion temperature and thus reduce the NOx emissions. However, running the combustion lean makes it very susceptible to combustion instability. The Rayleigh Criterion is the basis for analysis of thermoacoustic combustion instability and is evaluated using the Rayleigh index over one cycle of instability, where Q is the heat release rate perturbation and P is the pressure fluctuation. When the heat release oscillations are in phase with the pressure oscillations, the Rayleigh index is positive and the magnitude of the thermoacoustic instability is maximized. On the other hand, if the Rayleigh index is negative, then thermoacoustic damping occurs. The Rayleigh criterion implies that a thermoacoustic instability can be optimally controlled by having heat release oscillations 180 degrees out of phase with pressure oscillations at the same frequency. This minimizes the Rayleigh index. See also, references. Further reading, Poinsett, Thierry. Vainanti, Dennis. Theoretical and Numerical Combustion. European Centre for Research and Advanced Training in Scientific Computation. Lachner, Maximilian. Winter, France. Agrawal, Avinash K., Ed's Handbook of Combustion, 5-volume set. Wiley VCH. ISBN A978-3-527-32449-1. Balkall, Charles E., ed. Oxygen Enhanced Combustion. CRC Press. Glassman, Irvine. Yetter, Richard. Combustion. Turns, Stephen. An Introduction to Combustion, Concepts and Applications. Ragland, Kenneth W. Bryden, Kenneth M. Combustion Engineering. Balkall, Charles E. Jr., ed. Industrial Combustion. The John Zink Hamworthy Combustion Handbook, 3-volume set. Gardner, W. C. Jr. Gas Phase Combustion Chemistry. A.